Welcome to the Contagious Code Podcast, where we dive deep into code, learn practical skills, celebrate the beauty of engineering, and eliminate imposter syndrome. I'm Tejas Kumar, and I've been building on the web for over 20 years at places like Vercel, Spotify, Zeta, and more. Today on the podcast, it's a solo episode. I'm just going to be talking to you for a long time about AI innovation in 2025 onwards. It's exciting because we're going to start at the top and then go deep. We're starting at just like what even is AI, and at the end we're going to be talking about model context protocol and how you can build your own model context protocol server and client to share tools across AI agents to have them perform actions on your behalf. It's a really action-packed episode, and I'm so thankful I get to give. I love lectures, and I want to do more of these on the podcast. So if you feel the same, let me know on socials, at me, or leave a comment on YouTube. And if not, then also add me and let me know, and we'll prioritize guests. But frankly, this is just so much more fun because I love talking and I love sharing knowledge. Before we get into it, I need to emphasize, hey, this is very separate to my day job. And the way we can even do this is through the support of partners and sponsors. Let's take a moment and acknowledge them. The Contagious Code Podcast is partnered with Codecrafters. Codecrafters is a really great way of learning a programming language and a tool by building a tool in the programming language. Okay, what does that mean? Well, we all use tools as programmers. We use Git, we use Redis, we use Docker, we use VS Code, we use a bunch of things. And what Codecrafters does is it has you choose a language, so like Java, and a tool like Git. And it has you build that tool. It holds your hand as you build that tool in the language. And by doing that, you get better at the language and the tool. It's a really great way to learn. They have a generous free tier, but if you want to start paying, you can get a massive discount using the link in the show notes. That's tej.as/codecrafters. The Contagious Code Podcast is also partnered with the JS Heroes Conference. This is a conference happening at the end of May, so soon in Romania, and it is the best JavaScript conference in Europe, no question. It's large, it's nonprofit, it's transparent, and there's always value added. The talks are tremendous, and you learn a ton. I'm moderating this conference along with my dear friend and former podcast guest Anjana Vakil, and I'd love to see you there. JSHeroes.io. There's also a link in the show notes for that. Thanks for sticking around. Let's get into it. Okay, so let's talk about AI and AI innovation. And what we're going to do is we're going to get you up to speed to today from nothing. So this is March 2025, and we're going to assume you know nothing about AI. We're going to start at the top, at the surface level, and then go super deep together. And I think it just works better that way, because if you are a newcomer, then this is great to start with, and you will go on a journey to depth together. However, if you're like super deep in AI and you know everything already, stick with us for a few minutes or skip ahead, and we'll also cover some deep stuff that maybe I would challenge not everybody knows, even if you've spent some time in AI. So with that, let's just start right at the beginning to establish a common understanding together of what AI even is. So what is AI? And this is a good question because AI is, I'll tell you what, it's not new. It's not new. Especially if you want to know if AI is like a new thing or not, talk to a game developer. One of my dear friends, a game developer here in Berlin with a studio, they actually have a game coming out soon. I asked him, I invited him to my AI meetup. So I run a meetup in AI in Berlin. And I said, hey, do you want to come to my AI meetup? He said, yeah, I would love to. I'm so there. And he said, I'm really interested in AI. And then he continued to clarify specifically the generative stuff is what he said, right? And that's his take on it, because he's a game developer. And if you look at games, AI is not new. AI has been going for decades and decades, all the way back to Pong and Mortal Kombat and Pac-Man. Like, it's all artificial intelligence. Like how you play against the CPU Sub-Zero and he fights you in Mortal Kombat, like that's AI, right? And so it's not new. It's been around for a long time. However, the newer kind of AI is generative AI. Previously, AI was more rule-based. So you still have artificial intelligence. You still have intelligence that is simulated, but it's simulated by programmers literally just writing an algorithm. After this many milliseconds in the game loop, punch, then kick, then dodge. Or when the user presses punch, then dodge. Like it's event-based and it's rule-based. When this happens, do that. If the ball moves to the paddle, move the paddle close to the ball, right? Or to where the ball's going to be. So it's just algorithm. That's an example of rule-based AI, and it's been around for a long time. Eventually, we got We also used AI for like statistical modeling. The Markov chain is a great example of predictive statistical AI, where you use the current state of a system to predict the next state based on a list of possible states. Like if we think of the weather as a system, then you've got today's sunny, but all the possible states are cloudy, rainy, hailing, snowing. Based on today's state, sunny, we predict the next one, cloudy, right? The thing about Markov chains is they're characterized by the Markov property, meaning they don't have memory. And this is all the difference. So generative AI, or the kind of AI that's in vogue today, has what people would call attention, which is literally just modeling attention. It's what they've done, what researchers and scientists, mostly Google scientists, have done in their paper called Attention is All You Need, which you can find on the internet and maybe in a link around this video or audio. In their paper, they literally outline how they've been able to model attention algorithmically. And they call it multi-headed attention, right? Meaning with an algorithm, you can pay attention to a given word or token, which is either one English word or a partial English word, and its surrounding context. And because of multi-headed attention and contextual multi-headed attention, you can, with more accuracy, predict the next word or token. Token, again, is roughly equivalent to one English word. This is literally the basis of at least text-based generative AI or language-based generative AI. And this is the shoulder on which ChatGPT stands and other generative AI applications like Claude and other foundation models like Mistral and so on. So this is the stuff. Attention is all you need, and modeling attention. In this model architecture, it's an 11-page document, by the way, this paper. It's not too complex. In this paper, they show you a diagram, an architecture diagram of the transformer architecture that models attention. And in this architecture, you see that there's one layer dedicated to non-linearity. Non-linearity meaning, for lack of a better, in a crude way, meaning randomness, meaning novelty, which leads to novel outputs. And of course, this is configurable with temperature. Yeah, how creative or rigid do you want the output to be? And so I say that because that's the basis for hallucinations. Hallucinations are a quality of language models where they make stuff up, where they don't see the truth, where, for example, Google in their early version of their AI overviews feature would hallucinate results. You would ask, hey, how many cigarettes should a pregnant woman smoke per day? And it would tell you a pregnant woman should smoke between 10 and 15 cigarettes per day. Like completely hallucinated, because the training data contains jokes and satire, and it works with the non-linearity layer to create novel output, interesting output, generative, literally generated ex nihilo, or ex, not ex nihilo, but ex training data output. And so hallucinations in many ways are by design of the transformer architecture and are not a bug. But that said, they start to become functionally a bug in the real world when you can't trust the output of a model that appears to have some authority, or a model that we ascribe authority to. We're built this way. Like, we're used to Googling and trusting the search results, mainly because of Google's domain authority mechanisms, right? Google itself ranks domains based on authority, like .edu and .gov domains are automatically prioritized because they're supposed to be trustworthy sources, either educational institutions or government institutions. And so because they've created such an awesome algorithm that lends itself well to trustable authority, we've taken this thought pattern and applied it to language models, And so now when they output something, we just think this is the same credibility as Google, when oftentimes it may not be. It may be hallucinated, right? And so that's one of the problems with generative AI, is that it can hallucinate and show you things that either aren't true or are slightly false, which I guess would be aren't true at all. So that's one of the biggest problems with generative AI, is hallucinations. You can even see hallucinations with not just text-based language models, but also text-to-image models, where you say, draw me a picture of so-and-so, and it gets something completely wrong. I think probably the best example of this is it won't even be able to really draw you, right? And so that's kind of a problem, unless you add like very specific LoRa's. We'll talk about LoRa's maybe later. And so hallucinations, big problem with generative AI. Okay, what's another problem? Context, limited context. So after a really long conversation with a language model, say 25, 50 messages, depending on the model, it starts to get many things wrong. And that's because the window of context doesn't extend very far. It can only maintain a specific number of tokens or rough English words in contextual memory. And as a consequence of this, you're not going to or it is not going to remember information past a certain threshold of messages. And so you could be having a long conversation of the miracle of life, right? Single cell division, embryo, central nervous system, twins, and at some point things stop making sense because context has gotten lost. That's a really big problem, especially for very significant conversations where you would hope that context is long. Now, there's been remediations and innovations against this. Like some language models have very long context windows. Models like Gemini, or actually, I think Gemini has the longest with 2 million context. It's 2 million English words roughly, which is a good amount of context. However, it's still limited. It's still finite. Like if you think of human beings, we also have limited context, but we have long-term memory, which maybe limited, yeah, but it lasts like 60, 70, 80 years. Do you have any idea how many tokens that would be? A lot. And so we're nowhere near that with generative AI models. Another limitation of generative AI models is the fact that they have knowledge cutoff. Like when you train a model, what you do is you just optimize billions of little dials of probabilities to reach an outcome or an output a set of output tokens. These dials are called parameters. And for example, DeepSeek? The largest DeepSeek model has 671 billion parameters. Think of this as 671 billion little knobs that you can turn from 0 to 1 with some precision to get the right output. And the training process is learning to adjust each of those parameters to the right specific value so that you get the right set of output. The quick brown fox jumps over the lazy, being input tokens. Then there's 671 billion little dials to turn to arrive at dog. The quick brown fox jumps over the lazy dog. 671 billion parameters in the middle. The training process is just setting all of those to the right values and then freezing them. And then you have a model. That's literally like DeepSeek, the model, DeepSeek, the biggest one, is just that. It's like 671 billion values or parameters that are finely tuned to get the right set of output tokens for any given input token. That's a model. The reason I'm saying this is because models are frozen. Once they're finished training and they're tested, they don't like adaptively change like the human brain. They don't like receive a stimulus, learn, and immediately are updated like the human brain, right? There's a training process, and then they're saved as snapshots, and then you can run inference against them, meaning you can like generate stuff, but they're not like dynamic where they change. So they're static. So because of that, like if you finish training the model in October of 2021, and then you ask it for information about September of 2024, it doesn't know. It doesn't know because it's not part of the training data. So these are the three big problems with generative AI. Again, number one, hallucinations, just seeing stuff that's not there, making stuff up, just not knowing and pretending, or we call it pretending. Number two, being able to maintain a limited amount of context at any given time. And number three, having knowledge cut off because the training finished earlier than when you want an answer for. You're asking a question about 2023, the training finished in 2021, it just doesn't know. Okay, so those are really the big problems with Gen AI. There's a few other things that some would say are problems, but are really just not features. Like they're not problems because they don't harm anyone, but we want generative AI models to do more than they can currently. Those are missing features, but they're not necessarily bugs. They're not problems like hallucinations, right? Some would say that's really like a bug. Okay. And so with that context, how might we fix some of these problems? How might we fix some of these problems? Well, the answer is there is actually a silver bullet that solves all of these problems. All of these. And for those of you seasoned AI engineers here, you may be thinking, what is it? The answer is RAG. It's a technique called RAG, Retrieval Augmented Generation. It means to retrieve and then augment or change the generation, the generated output. We're not creating a new model. The model is static. We just said this. The model is a set of parameters. It's static. But we are retrieving data from just the internet, from an authoritative source. It doesn't have to be the internet. It could be a PDF, it could be a classified document, it could be literally anything. But we're retrieving this data from somewhere, and we're using this data to augment the generation. How can we do that? Well, really, RAG finds itself in another discipline called prompt engineering. So RAG works like this. You say in your prompt, here's the latest data, and you literally just like put the data in there. You get it from you retrieve it from somewhere, you put it in your prompt. Here is the latest data, and you put it in your prompt. And then under the latest data, you say, now based on this, answer me these questions, and then you include questions. And then the language model, like the parameters don't change, the model doesn't change, but you introduce new context. You literally get data from somewhere authoritative, you retrieve it, and you put it in your prompt. And by doing that, you give it the information conversationally. You're like, here's information, now answer questions. And so you're retrieving data, you're putting in your prompt, and you're using that context to augment the generation, the output. Does that make sense? So let's make this practical with like a real example. Say you want to use your language model assistant to help you convert currency. You have $100, you want to convert it to Indian rupees. So how might you do that? Well, the language, if you literally try this with a typical language model, you'll say, hey, help me convert 100 USD to INR, Indian rupees. The language model will say, as a language model trained by OpenAI, I don't have that capability. Why? Because, well, it needs to retrieve from the internet today's current exchange rate, and then it needs a calculator. It needs to be able to do math, which language models typically are great at language, but poor at math. And so the language model will say, I can't browse the internet, I can't do it. Now with RAG, you would retrieve that data from the internet. You would literally be like, in your prompt, today's exchange rate is 1 USD equals 1,104 INR. Now convert 100 USD to INR. Like you would retrieve that from the internet, put in your prompt, and then submit your question. That's RAG. You retrieve, put in your prompt, augment the generated output. That's actually basic RAG, and this works for the vast majority of cases. For example, you could ask a language model, and I'm saying language model, not AI application here. We'll talk about this in a minute. You could ask just a model that had its training completed in 2021. You could ask, which movie won the Oscar for Best Picture in 2024? And it would give you back an answer. I don't know, my training cutoff is 2021. This won't work in ChatGPT as it is right now, because ChatGPT is not just a language model, it's an application that performs RAG. ChatGPT actually performs RAG. Like if you ask this question to ChatGPT, it will search the internet, construct a prompt, feed the prompt to the language model, and then give you an answer. Like ChatGPT is a great example of RAG, okay? But if you ask a language model, which movie won the Oscar for Best Picture in 2024, and this language model finished its training in 2021, it's not going to answer you. So then you would perform RAG. You would literally like write a script, JavaScript, Python, whatever, to go to the internet, find a web page that has the answer, get its contents, text content, put that text content in your prompt, and then ask the question. Here's context. Now, which movie won the Oscar for Best Picture? That's literally RAG. RAG is great, and it solves so many problems. So many problems. It does fall apart, though, with other areas. For example, RAG fixes hallucinations because you literally like give the answer in context and you ask a question, right? And so hallucinations don't exist very much with RAG. What problems can occur with RAG, though, is your context window is too small. So you could fetch an entire web page and include it in your prompt, but if the web page is very large, for example, the HTML language specification is 25 megabytes. It's a very large document. You can't include this in a prompt, right? Because you're only allowed a certain number of input tokens, again, roughly English words. And if you exceed that, the language model will reject you. It can't handle such input. So RAG can't help you in this case the way I just described it. How might you optimize for RAG in a more profound way? What you would do is actually still retrieve the text content, for example, of the HTML specification, a large one, but you wouldn't inject this into your prompt. Instead, you would take the text content and do something called chunking. That's exactly what it sounds like. Literally, you take a massive document, like 200 pages, whatever it may be, and you break it down into chunks. That's what chunking is. You could say a chunk is roughly 1,000 characters or so. And you could say that chunks have like 50, 20 characters overlap between them, so that they have some crossover between heads and tails of chunks. And so you break down your huge document into chunks of a size that you choose, roughly 1,000 characters, whatever it may be. And then you store these chunks somewhere. And then when it's time to perform RAG, instead of going and dumping the entire web page in your prompt, you just query for similar chunks that match the user's query. Let's make this really practical with an example. The HTML language specification is a large document. It contains information about every single HTML element available. Some examples of HTML elements are div for divisions like blocks, spans for single lines, spans of text, images for, well, images, video, etc., details, summary, all of these paragraph, all of these are HTML elements. And there's many, many, many of them. And the document outlines not just each element, but what it is, when to use it, what attributes it has. It's a huge deal. So say you wanted to ask for, hey, how do I correctly represent an emoji in HTML? Right? This is your prompt. The RAG flow, you can't dump the entire HTML spec into the context, in the prompt, as you mentioned. So how can you work with this in RAG? Well, you chunk the entire document, store it in your database in chunks, in some storage system. And then what you do is you, based on the user's query, how do I accurately represent emojis in HTML? You take that query and perform a similarity search across all your chunks. You find the chunks that are the most similar to the user's query. Chunks about emojis, image accessibility, etc., that come from the HTML spec, right? So chunks of the document that are close to the user's query. You find those, maybe the top 5, top 10 chunks. You include those chunks and those chunks alone in your RAG prompt as context. And then you answer the question. So your prompt is, here's some context, and you pull out the 5, 10 most similar chunks of this large document. And then you say, now answer the question, how do I accurately represent emojis? That's how you get over this finite limited context window. Now, where do you store these chunks? I guess that's the question. And this is where we need a vector database. A vector, okay, what is a vector database? To understand vector databases, we need to understand vectors in general. Okay, so what's a vector? A vector in math is a list of numbers. Congratulations. Like it's literally, it's a list of numbers where the numbers represent two things. They represent direction, so left, right, up, down, maybe, and they represent magnitude. How much in this direction do I go? I think a great example of vectors is coordinate systems on a map, right? Two-dimensional vectors, that's a coordinate system. So 51 east, 27 north, that's roughly somewhere in the Middle East. I think that's like Saudi Arabia, Dubai, something like that. That's how we know where to put things in the world. This coordinate system, that's a two-dimensional vector. So how many dimensions? 2 dimensions. What are the 2 dimensions? Up, down, that's one. So y-axis, and left, right, that's another dimension. So you got 2 dimensions on a map. If you add space or depth, for example, if we're not just navigating on the surface of the Earth, but we're navigating towards the Earth's core, then you would add a 3rd dimension, depth, right? And so you have now up, down, left, right across the map, but also how deep inside the Earth. That's 3 dimensions, so, right? And I hope you're tracking. And so that's just a 3-dimensional vector. Left, right, up, down, and inside, out. It's 3-dimensional vector. So vectors are literally just lists of numbers that convey direction and magnitude. Okay. How does this tie in to a vector database? Well, a vector database is a database of vectors. It's a database that's specially purpose built to store large lists of numbers. We already talked about 2-dimensional vectors, 3-dimensional vectors. In the world of AI, we also work with vectors, but in terms of dimensionality, these are high dimensionality. Like I already used a map as an example, left, right, and a 3D space as an example. In AI, vectors are of the order of like 1,000 plus dimensions. Like there's no real way you can conceptualize this. Like you can conceptualize 2-dimensional space, 3-dimensional space, but how do you conceptualize like 1,000 dimensions? You can't, right? But I hope the map example was helpful. And so, what are vectors? We covered that. And so you take the chunks of this long document, HTML document, you break each chunk into vector embeddings. We'll talk about this. And you store the vectors in a vector database. The key missing point here is vector embeddings. Okay, what are vector embeddings? Say it with me. Embeddings, what a word. Vector embeddings are numbers that are embedded in space. Okay, this is starting to sound very crazy. Here, let's do a thought experiment. Let's do an example to make this very clear. I want you to picture in your mind a crosshair, literally a crosshair. So like an X or a cross, like a plus sign, a big plus sign, okay? And this plus sign is divided into 4 quarters. It's top left, top right, bottom left, bottom right. You seeing that? Cool. Now imagine a word: dog, cat, mouse, monkey, lion, right? These are animals. And so in this cross diagram, in this 4-way plus sign, pets and animals would be in the top left quadrant. Reptiles, crocodiles would still be in the top left quadrant, but slightly further away from things covered with hair, like dogs. Okay, but generally, animals, mammals, reptiles, they're all in the top left. Steel, aluminum, copper, zinc, these are in the bottom right. They're very far from the animals, but they're there. This is what embeddings are. So remember, we talked about vectors being things that convey that convey direction and magnitude, right? And so those are vectors. Embeddings are when you embed words or vectors in space. And so we're working here with our X, with our cross, with our plus sign in space, in 2-dimensional space. And we are embedding dogs, cats, reptiles, camels, birds, dinosaurs. We're embedding them in the top left quadrant. We're embedding metals, steel, and aluminum, and iron, copper. We're embedding them in the bottom right quadrant. Light, heat, sound. These things are waves. They travel over waves. We're embedding them in the bottom left. So we're just like taking things that are semantically close to each other and embedding them in space. Does that make sense? In 2-dimensional space here. Does that make sense? That's embedding. That's literally, so now you understand vectors, you understand embeddings, you understand vector databases. The final piece is how are these embeddings embedded in space? And this is where we have specialized machine learning models. These are not language models. They're certainly not large language models, but there are specialized models called embeddings models that can understand semantic meaning, natural language, and embed them in high dimensional space, and then give you back the coordinates, which are vectors. So in the case of our little plus sign, our crosshair, dog, remember dog? Dog was in the top left. So an embeddings model would read a word like dog and give you back its coordinates. Dog is here in space. And then you give it the word cat and gives you back coordinates. Cat is here in space. And those coordinates map squarely to the top left quadrant in our 2-dimensional space. But of course, they work in thousands of dimensions. But that's what an embeddings model does, is it receives natural language, gives you back coordinates. The cool thing is, these coordinates are always fixed length. They are always a fixed length. They are, by a fixed length, I mean they're either 1,000 dimensions or 1,536 dimensions, whatever. And no matter the input size, the output is always the same length. So you could do dog and get back coordinates, cat or get back coordinates, or the quick brown fox jumps over the lazy dog and get back the same length of coordinates, just moved slowly somewhere in that space. Does that make sense? And so that's how you do RAG against limited context. You break a large document into chunks, You convert each chunk into vectors embeddings, and you store those vectors in a vector database. Then when a user has an incoming query, you take the user's query, you find, you literally generate embeddings for the user's query. So you know where it sits in space. Then you find nearest neighbors in vector space to the user's query that represent some of these chunks from your large document. You pull out those chunks, you inject them into your prompt. You say in your prompt, here's some context. You embed those chunks in your prompt. And then you say, now answer the question, and you include the user's query. Then you get back an answer that is highly contextual based on the user's query and chunks of your large document. This is how you do RAG that prevents hallucinations and now also overcomes the limited context of large models. There's still issues with this though, because we miss keyword details. So far, we've been searching for chunks based on semantic proximity, meaning semantically, in terms of natural language, is this close to the user's query? But sometimes, instead of just is the meaning close, we need to include words from the user's query as well, right? If a user says, how do I represent emojis faithfully in HTML? You actually want results, you want chunks that include the word emoji. And if we search for similarity in semantic meaning, we don't search for exact word matches. And so this can often lead to problems. There's a great example here with medical documents that we can explore to understand where this falls apart. For example, if someone's searching for the best COVID-19 treatment protocol for immunosuppressed patients, in this case, semantic search may yield unfavorable results because it's capturing the entire meaning of the sentence as opposed to the keywords. And here, immunosuppressed is a very important keyword, right? And this is where we need an alternate approach. We can't rely on semantic search alone because our accuracy might be impacted. And so, okay, what do we need as a complement to this is we need traditional search. That's keyword search. Traditional keywords, Google is the greatest example of this. If you type in a word like pizza or best pizza in Berlin, Google will use keyword search to help you find that. And it will do that using an algorithm called BM25 or Best Match 25. And how it works is, we're not going to go too deep into the details of a search algorithm here because honestly, I think many of you are not as interested in the ones and zeros, but more in the mechanism, like how it works. BM25 is, if we think of it like an agent, like a librarian, if BM25 was a librarian, it would be someone who counts how often your search words appear in documents. So like if someone was searching for best pizza in Berlin, they would give really high scores to web pages that have exact matches. So if best pizza Berlin, if they have an exact match of that, awesome, you get a massive score. If the document isn't too long, this is literally part of the BM25 algorithm. If the document isn't too long, because you can then avoid rambling text, and this is also some like SEO tips for you as well if you want to optimize your search engine work. And then third, it will select for documents where your keywords appear frequently, right? But not too frequently because that's abuse. Early in the web, for my fellow millennials will know, you used to do this thing where you just like repeat words a lot for SEO to the point where you couldn't read anything. Even worse, a way to hijack search engines previously was you have white on white text separated by commas. And so users can't read this, but there's just words there, a lot of words that you're hoping search engines would read. All of this is abuse. And for that reason, the BM25 algorithm is very good because it optimizes for documents where there's enough keyword density, but not too much, right? So the three criteria really that BM25 will select for is number one, exact matches of phrases. Or keywords. Number two, documents that are not too long. And three, documents that repeat the keywords but not too much. So let's follow this up with an example. If you search for something like best pizza Berlin, this is how we search Google. I don't know about you. I don't type in like a natural language like, hey, please help me find, So if I go on google.com and I type best pizza Berlin, how's that going to work? Well, BM25, I don't know what algorithm Google uses to be fair, but if it's, let's not say Google, if I submit this query, best pizza Berlin, to a BM25 algorithm, then how it would choose what to surface is it would give a very high score to like a restaurant guide that uses the word pizza many times, 10 times, that would be a very good document to surface. If that document is like 50 pages long or just a very big document, then the score would lower. And if every single page says best in this document, then it penalizes it. Yeah, because if everything's the best, then nothing's the best, and this is some marketing hype. So this is literally how BM25 works. And so why that matters is you're matching on keywords, but also the use and abuse of keywords. Are the keywords too much? Are they overused? And so on. That's super important. In the case of a document, for example, going back to our COVID example, COVID-19 treatment protocols for immunosuppressed patients, well, then any exact matches of that, so COVID-19 treatment protocol plus immunosuppressed patient, any exact matches would rise to the top. If those pages are too long, then there will be a penalty. But if the important thing is it matches on the keywords. Does that make sense? It doesn't match on some interpreted meaning. It matches on those exact keywords. And this is a contrast to embeddings and vector embeddings that we literally just talked about, that match not so much on keywords, but on semantic meaning. And if in this case, if we ran COVID-19 treatment protocol for immunosuppressed patients through a vector search, exclusively vector search, we might get a bunch of COVID-19 treatment protocols. We might get a bunch of treatment protocols. We might get a bunch of immunosuppressed, immunocompromised patient treatment protocols that have nothing to do with COVID-19, because the weighting of each keyword is not substantial. It's more the weighting of the sentiment. And it sounds like you're just looking for a treatment protocol. Here's a bunch of treatment protocols. This is where vector embeddings can fall short. Does that make sense? And hybrid search is great because, or rather, keyword search is great because it prioritizes the keywords. Just again to recap about embeddings, it captures the sentiment. So for example, if you search just with the vector search for like puppy, then young dog works. Even dog works. If you search for tiny home with an embeddings model or vector search, then small house will be yielded. These are just different words, but that's how they work. Meanwhile, if you use BM25 or keyword search and you search for puppy, then puppy rises to the top, not small dog. Does that make sense? If you search for tiny home with keyword search, then small house is never. Does that make sense? So this is the difference between vector search, similarity search, and keyword search, which is usually powered by the BM25 best match 25 algorithm. So you could take, for example, one or two of these and combine them into what's called hybrid search. And this is really the best of both worlds, right? If we go back to the case of treatment protocols for COVID-19 patients who are immunocompromised, your vector search is going to yield you a set of results that may be inaccurate. Your keyword search is going to yield you a set of results that maybe aren't capturing the full semantic context. And so hybrid search is literally combining both of these, and then there's one more step that we'll talk about. But does that make sense? Like if we consider the query for puppy, right? Same thing. Vector search will give you young dog, or just dog if you don't have enough data. And keyword search would give you stuff that literally just matches puppy. And as a result, you have these two result sets that you got from somewhere. Finally, to tie them all together, you need something called re-ranking. And it's called re-ranking because you have two sets of results. You have a semantic similarity result with vector search, and you have a keyword density result with BM25 or with keyword search. And so you have these two result sets. They are ranked already. You concatenate them. These are my ranked results. And you present them to what is called a re-ranker. Okay, what's a re-ranker? A re-ranker is just like another AI model, believe it or not. It's just a machine learning model that is used for adjusting the rankings of a hybrid search result set. And so what happens is you present your both result sets to a re-ranker, and it will literally go through and understand, okay, hey, which documents here make sense, and will assign a score to them. For example, you could search for stainless steel fridge, or for example, even better, if you're searching for like a chef mixing ingredients, right? You could search for a stainless steel fridge with keyword search, or a durable metal refrigerator with embedding search. You get back a bunch of results. You combine them. You present them to a re-ranker, and a re-ranker is gonna give you a confidence score based on both. So what you could do, what a re-ranker might do, is take the BM25 score per document, which both algorithms BM25 and vector search give you a score. So it'll take the BM25 score, multiply it by like 0.6, plus take the embedding similarity score and multiply that by 0.4, sum those up and give you a total. This is the new ranking based on both search result sets. And so when you do that, what it's going to do is also then compare that to the user's query, right? And so this boosts accuracy so much. Hybrid search is the gold standard. It boosts accuracy by 45%, as we can see in some research. And so let's consider this. How would a re-ranker work? How would hybrid search work for pizza search? We've been. I'm so excited. I'm speaking faster than my mouth. We've been talking about pizza for a while. So if we take a search query, vegan cheese pizza recipe, we take this and we give it to a set of embeddings search or vector search and keyword search models. Then the vector search, vegan cheese pizza recipe, it could give us vegan recipes, it could give us vegan cheese recipes, it could give us pizza recipes that are not vegan. Similarly, if we give the same vegan cheese pizza recipe to a keyword match, it will just give us vegan cheese pizza recipe documents and rank them accordingly, but it may not capture like the broader context, the feeling of it, okay, and the semantic meaning of it. And so what's going to happen is let's actually walk through this perfectly. Instead of the recipe, even let's look at a real example. I don't know how many of us cook, but I know a lot of us eat. And so if we look at the example of you're searching, hey, where can I find vegan pizza near me? Vegan pizza near me. If you give this to a BM25 keyword matcher, then it will find the best pizza in Berlin. Vegan or not, it doesn't matter, because what's happening? Pizza near me or pizza Berlin is amplified, and pizza is mentioned 5 times, and so that's probably going to be at the top. Again, because it ranks documents that repeat keywords not too many times, but repeats keywords and especially exact matches of keywords to the top. So BM25 is going to yield you like one result, best pizza in Berlin. Second result is a vegan bakery menu near me. Here's a vegan bakery near me, right? That's how these things work. So result number 1, best pizza in Berlin. Result number 2, vegan bakery, which is not pizza. And so what am I supposed to do with this? Well, the first result mentioned pizza, the second result mentioned vegan. We have that. Now you give the same query, vegan pizza near me, you give the same query to semantic search or vector search model, and you get back a plant-based Italian restaurant. Notice I didn't use the word Italian restaurant. I didn't use plant-based, I used vegan, but again, this is capturing the vibe, not the words. So it will yield you like, here's a plant-based vegan restaurant near you, or Italian restaurant near you. And it will also yield you, here's some dairy-free dining options. So the BM25 gets you the best pizza and the vegan bakery. The embeddings gives you a plant-based Italian restaurant and a dairy-free dining option near you. And both of these are like, okay, cool, but like, which one is vegan pizza near me? This is where hybrid search makes it better, because it re-ranks everything. It literally looks at all these results and then ascribes them a score that is relevant to your query. And the re-ranker will literally check, okay, now which of these actually serve pizza based on the returned results, which are truly nearby, because you said near me, and which have good vegan items or reviews, or does it say vegan somewhere in this returned corpus of text? The re-ranker is going to do this and then assign a score to your result sets, hence re-ranking them, and ultimately gives you the most accurate results. And so that's how hybrid search works and can solve this problem. So far, we've spent a lot of time talking about RAG, the technique to introduce new context to a model and real-time information. And some of you wizards out there might be thinking about a question that's been on many people's minds, and that is, okay, that's RAG, but I heard somewhere that fine-tuning is a thing. You can fine-tune a model and give it new information, extend its training data that way. And so there's been an ongoing debate for a very long time among enthusiasts, RAG versus fine-tuning. To understand this, we've spent a good amount of time talking about RAG. Let's spend a good amount of time talking about fine-tuning. What is fine-tuning? Machine learning models, as described earlier, are their systems, their architectures where they receive inputs, and then the inputs are passed through many layers of billions of parameters, little dials, and there's an output layer where the probabilistic outputs, the most probable outputs, are aggregated. Ultimately, you get one. Set of tokens as a output. And so these layers, 671 in the latest DeepSeek R1, the biggest one, 671 billion. When you fine tune a model, you change the there's two ways. One, you can change the weights, or two, you can actually add layers. So instead of 671 billion, there's 700 billion, and that's actually what happened between like GPT-3 and 4. Is just you add new layers. If you add new layers to a neural network, essentially, metaphorically, the brain gets bigger and there's more information, right? Okay, that's very hand wavy definition of fine tuning. Some ways of fine tuning are efficient. They use things called LoRa's, which are low ranking adaptations. We're not going to get into all of that. We may do an episode in the future on that, or we might do it with a guest. Suggest what you want in the comments. But when you fine tune, you fundamentally add new information is by way of layers, or change the weights of a model. With RAG, the model stays as is. This is very important. With RAG, the model, you never touch the model. The model is static. It's a set of weights. It doesn't change. And you introduce new context only through your prompt. With fine tuning, the model itself changes. It becomes a new model. GPT-3 becomes GPT-3.5, becomes GPT-4. And new models have new capabilities because there's more parameters. For the case of getting real-time information, would RAG yield better results, or fine tuning yield better results? The answer is RAG would yield better results. And there's multiple reasons for this. Reason number one is that fine tuning is just very expensive. Like very expensive. You require very expensive hardware. GPUs are not cheap, and you require many of them just to run the training workloads. The oldest, like, attention is all you need paper that we cited earlier, I believe it took a few days and 8 GPUs running concurrently, right? And so it's not an easy thing. So it costs in terms of time, in terms of hardware, and in terms of compute, and in terms of electricity. It's just extremely resource intensive. And as part of the training process is performing what are called evals, or evaluating that the model actually works the way you want it to. That is also expensive because if you've not tuned some hyperparameters, these are parameters for the training process, like learning rate, epochs or epochs, and things like that. You need to tune them well, and if you've not tuned them well, then after a lot of training, you could have a model that yields really poor results, and you've wasted time, energy, compute. And so it's just laborious. And for what? Meanwhile, with RAG, you just get context, put in your prompt, it's done. And you can just adjust your prompt, which is way cheaper, even free, compared to creating a new model. So RAG wins. There's another reason why RAG wins, and that's because these are language models. Fundamentally, these are large or small language models. And in terms of what they generate and what they're trained on, is not really information and facts. It's language. And this is, you can see this with the hallucination problem, right? For example, Google's AI overview feature had people asking, hey, how many cigarettes should a pregnant woman smoke per day? And because it's good at language and not information, it said, pregnant women should smoke 3 to 5 cigarettes per day. This is like Google it. This is an actual thing that happened. Misinformation on google.com with the AI overview feature, because they're good at language, not logic, not information. Yeah. And so you can use RAG to help with logic and information by giving authoritative information in your prompt. But you can't fine tune information into the model. It is a language model. It transforms contextual input tokens to contextual output tokens. It's not logical input tokens to logical output tokens. It's contextually aware input tokens to output tokens. And so you start to see, okay, well, language models are great at language, not information. So here's the rule of thumb. For information, RAG is the best choice always. For correct and accurate data, real-time data and information, RAG is the method. Fine-tuning is not wrong. It's just, if you're after real-time information and correct information, it's not the best, because ultimately a language model will always output language and not logic. So RAG is your super weapon there. Fine-tuning is good indeed. it's good for other things. For example, it's good for enhancing language capabilities. If you want a model to have better context, a better grasp, of nuance between terms, then you fine tune. If you want to teach a model a new language, Klingon, Amharic, Azerbaijani, whatever, I'm just like an alphabetical order, Zulu, Xhosa. If you want to teach it these languages, right, then you fine tune because it's language. It gets better at language. If you want to teach it a programming language, binary, assembly, Go, Rust, Java, Python, Scala, maybe you, like Keel, you have your own domain-specific language or DSL. In that case, you want to fine-tune. No amount of RAG is going to get the right grammar of the language every single time, right? There will always be hallucinations because of the training data. Does this make sense? And so this is the answer for RAG versus fine-tuning. Is RAG is great for actual, authoritative, accurate, correct information and data and logical data, and fine-tuning is appropriate for language and so on. Fine-tuning, and the other benefit of fine-tuning while we're here, is also for saving money and compute, right? Because these language models are very large usually. Again, as I mentioned multiple times, DeepSeek R1, the biggest version of DeepSeek, is 671 billion parameters. Do you need all those parameters? For general use cases, yeah. If you have something like ChatGPT and you want it to be used by 100 million users and so on, you probably need a lot of parameters. But if you're a bank, a hospital, an individual, and you want a language model specific for your use case, like the podcast search of this podcast on tej.as, you probably don't need all those parameters. In fact, the more parameters you have, the more that can go wrong, the more that can be hallucinated, the more nonsense is in those parameters, yeah? And so you may need smaller models. You may need smaller, instead of LLMs or large language models, you may need SSMs or SSLMs, small specialized language models that cater to your specific type of language. For example, the podcast search here is A/B tested with a smaller language model that doesn't really speak anything except HTML and a little bit of podcast language. It's a combination of RAG and fine-tuning that saves a bunch of money. Because the larger the model, the more expensive it is to run. The smaller the model, it's not. One of the best small models that you can use, it's open source, is Mistral 7B. There's only 7 billion parameters. That's 100 times smaller than DeepSeek R1, roughly, right? And if you can fine-tune Mistral 7B, it'll probably have a little bit more than 7B after it's fine-tuned, to your specific use case, then you have this awesome model that you can run for your specific case very cheaply, and even on your M1 MacBook Pro, right? And so fine-tuning is not without its benefits. It's very good. It's just you need to pick the right tool for the job. And again, I will say this again, for data and correct information, it's RAG, and real-time information, it's RAG. And for anything language-related or compute-related, the size of the parameters, fine-tuning is better. Finally, I'll stop this discussion with this. It's almost never one or the other. Never ever one or the other. A lot of people even do this with web stuff. Should I use React or JavaScript, which is such a strange argument because React is JavaScript, and it's usually you use both and you use them well. You use both with RAG and fine tuning. If you want to do production grade enterprise AI at scale that's reliable and guardrailed, you probably want to do both. You will bias more towards RAG just because it's cheaper, but over time, when you want to save costs, you will do fine tuning. In fact, we have a really great podcast episode with John McBride. We'll put a link to that in the show notes, where he talks about how they fine tuned Mistral 7B at OpenSauced, which was later acquired by the Linux Foundation. And saved $30,000 a month or something. It's a really great episode. We'll put a link to that in the show notes as well. But for our discussion on RAG and fine-tuning, I hope this clarifies what to use when and how. Okay, so now that we've cleared up RAG and fine-tuning for getting accurate data out of LLMs, let's circle back. We talked about hybrid search and how all of this works together. And we talked about hybrid search as parts of a system. Again, these parts are part A, you have vector similarity search, part B, keyword search, part C, a re-ranker, which takes both search result sets and ranks them for accuracy and novelty and correctness. And then finally, like an LLM part D that gives you the results, right? So we talked about them as parts of a system. Another word for parts of a system, if we stretch a little bit, is agents. What we just described is in software, you could just describe this as an algorithm. You could write the code. You could write code to perform vector similarity search. Then you could write another function to perform keyword search. And then you could write another function to re-rank and another function to return text. You could do these as functions. But the world is changing. And what formerly were functions and code now find themselves as AI agents. And we're moving this way. And so I think this is just a natural segue to talk about agents in 2025. Everybody, like the year started with people saying 2025 is the year of AI agents. 2025 is the year of AI agents. What does that even mean? And who starts a conversation this way? So I think it helps to understand and orient ourselves in the current moment. The state of AI agents, talk about them a little bit. We already looked slightly at how they can do things like implement hybrid search, for example. And then we'll have a better understanding of agents, and then we can talk about the real thing that's in vogue, which is model context protocol and how all that works. Okay, so let's start by just talking about agents. And if we start our conversation about agents, let's just start at the beginning. Let's start like at the basis of everything. What is an agent? Well, I am an agent of chaos. No, I'm joking. No, I am an agent. You are an agent. We're all agents. Okay, what makes us agents? The fact that we have agency. The fact that I can exercise agency and choose to record a podcast. I can choose to talk to you. I can exercise my agency to talk to you, to record this, right? That makes me an agent. Where else might we encounter this word in our daily lives? Well, travel agents, yeah. What do they do? Well, you call them on the phone. You talk to them on the internet, I don't know, however your modality is, and you say, hi, I'd like to book a flight from here to there, or a train from here to there, and they do the job on your behalf for you, and then they send you a confirmation, right? They're agents, and they literally have agency to work for you on your behalf. Does that make sense? That's fundamentally like the definition of agent, irrespective of AI or not AI. Like that's just agents. Things, people, entities that can exercise agency towards an outcome, sometimes acting on the behalf of others. That's the definition of an agent, okay? In the context of AI, what does that mean? Well, language models are great. They can talk a lot like people. They're literally artificially intelligent to that extent. But so far, they haven't had the ability to act on one's behalf. And in 2025, that's changing, and in fact has changed. And so what is an agent? An AI agent specifically, is when an AI can exercise agency. And some of you listening or watching might be thinking, okay, but like they can do that already. Like you say hi to ChatGPT, and then it exercises agency over the next output tokens. That it says, hi, how are you? Something like that. That requires agency. Absolutely, it does. But there's another level of agency that is not yet unlocked with language models, or that is slowly becoming more and more common, which is agency over the use of tools. Like in the human story, that's where things got really cool for us. Right, and by us I mean human beings. Where, we're I don't know, we're cavemen. We're doing our thing. I don't really know what cavemen did before tools. Anyway, at some point we decided, hey, I'm gonna make like an arrow, a spear. I'm gonna take these stones and like make tools for myself. And then we built tools, and then we started to use tools. And this is a game changer. Like literally right now, you could ask me, hey, Tejas, give me the dot product multiplication result of 18 prime numbers. and I'm going to give you the prime numbers now, right? I'm going to be like, no, because I can't do that off the top of my head. So I will say no, but also I'll think, wait a second, there's a tool that I can use for this. It's called a calculator. And so if you really wanted me to do that, I would go find a tool and use it. I would exercise my agency. Let's pay attention. I would exercise my agency to choose the tool and then use the tool. And what do most tools have in common? They have interfaces. We interface with. How do you interface with a calculator? Well, there's buttons. So your interface enables you to give input to a tool. Okay, so you give input to the tool through it, and this is true for literally any tool. A hammer, the interface is the handle, and you give input by exerting force to hit down. Yeah, a keyboard, it's you interface with the computer. You get the idea. So, continuing with the calculator, we interface with the calculator through buttons. We generate the input though for the tool. This is so important. We generate input to the calculator from our language model, our brain, literally. So like if you asked me, hey, sum or multiply 13 and 27. I don't know if 27 is a prime number, correct me in the comments, but multiply 13 and 27, I can't do that off the top of my head. And so, yeah, some of you are judging me, whatever. What I would do is I would find a calculator and I would use the interface. What's the interface? The buttons. And my brain would say, okay, enter 13 as argument 1, and then press multiply and enter 27. So I'm generating the inputs. My brain is generating the inputs to this tool, and then I hit equals and I get back a result. In fact, let me see if I can pull up a calculator right here. 13 times 27, that's 351. Okay, I just used a calculator. 351. And so I see that, I receive that, my language model receives the output of the tool as my input, 351. And now I tell you, I generate new language with my brain. Okay, the result is 351. That journey is exactly what is replicated with language models like GPT-4 and Claude 3.5 and 3.7 and Gemini, and that's the basis of what we mean when we talk about AI agents. I hope this is so clear. Does that make sense? Having agency over choosing a tool and then using the tool by generating inputs from the language model to the tool, receiving the tool's output as part of conversation history, and then synthesizing output language. This is completely now replicated with language models like GPT-4, Claude, Gemini, DeepSeek. Actually, DeepSeek can't do this, but it's completely replicated. So that's what we mean as tool calling, function calling, or tool use, and that is characteristic of agents. Does that make sense? And usually these tools are external. Okay, but now some of you might be thinking, what do these tools even look like? Because a calculator is a physical thing. A hammer, a screwdriver, a drill, a car, a keyboard. These are physical things. How do language models use these? As far as I know, the robots can't, And so, okay, first of all, robots can use hammers. Google it if you want to be scared. But second of all, the tools with language models, which are software tools. Okay, well, how do software tools manifest, if not through physical interfaces? Software tools are functions. They've been around for literally decades and decades, right? Functions. For those of you programmers listening, you could write a function to perform a multiplication, right? You literally, what programming language? Let's do JavaScript, TypeScript. I'll just dictate it for you. You write function space multiply parenthesis x comma y close parenthesis open curly return x star y close curly. Yeah, that's a function that does multiplication. That you're able to give this to an LLM, and it will execute the tool and give you the result. That's a tool. A function is a tool, and a tool is a function with a little bit more. It's not just a function, but there's additional metadata. Specifically, the metadata are twofold. One is the description of the tool. What does this tool do? When do you call it? And that description is just plain language. It's just English. And this is how the LLM knows when to call the tool, because the description of the tool says use this tool when so and so. So if we were to describe a calculator, it would be a big JSON object, and it would have three properties. It would have description, which is a plain text string of what it does. So you would say something like, this tool is used to add, multiply, subtract, divide, square root numbers. That's a description. Then you would have the schema, the input schema. And this is either JSON schema or a XOD schema. It's some type of schema, an object that describes, okay, the inputs are X, which is a number, and Y, which is a number. or maybe an object of properties X and Y, something like that, input schema. And then you have the actual implementation, the function. And the function is just a programming, it's literally just a function that can do an operation and return a result. And the result is usually something that the language model can then receive and quote unquote think about, and then continue the conversation with. That's a tool. That's literally a tool. And LLMs can now use tools, just like early humans, to do stuff. Agents, AI agents specifically, use tools. Here's a blanket statement that may be controversial. All agents, artificial intelligence or natural intelligence, use tools. That's a thing. And so that's one of the characteristics of agents. They can use external tools that are provided. Okay. There's a paper by Google released in September of 2024. The paper is literally just titled Agents. And I'll put a link to that paper in show notes. And this paper takes the definition of agents a little bit further, talking about agents as a runtime. Okay, what's a runtime? A runtime is it's an execution environment for code. I'm laughing because I was gonna say, well, it's a time in which you run, but that's not true. A runtime is an execution environment in which code executes. Okay, so what are some examples of runtimes? Well, browsers. Great example of a JavaScript runtime. A browser runs JavaScript. JavaScript executes inside the context of a browser. That's a runtime. Another example of a runtime is Node.js. It's a runtime that executes on a server or a machine that runs JavaScript, and the JavaScript can then interface. It gives context to JavaScript. That's what a runtime is. A runtime is an environment in which code can execute that gives context to the code, to the code execution. So for example, in the browser runtime, you have the window object in JavaScript. Window.innerWidth will tell you how much the width of your window is. You don't have this context in the Node.js runtime. Window is undefined in Node.js because there is no window. Yeah, it's in the terminal. And so a runtime usually gives context to an application that's executing or code that's executing inside the runtime. And so Google's 2024 paper says agents are a runtime, and this runtime has three elements of context, three pieces. It has tools. We literally just now talked about tools, just JSON objects that represent operations. It has a language model, or a model in general. And we also talked about this, where the language model generates inputs. Yeah, like for the calculator, my brain was generating the inputs to the calculator. So you have tools, you have a model. The third piece is an orchestration layer, is a piece of code, a program that coordinates the tools and the LLM. It just binds them together, the glue, so to speak, that receives a user's query and then sends the query to an LLM. LLM decides, okay, I need to call tools. Tools are called. That response goes back to the LLM. The LLM yields back to the orchestration layer, saying, here's some results. The orchestration layer performs validations. For example, if you want a JSON object, it would then validate this is actually the schema you wanted. It will perform a bunch of validations. And if the validations pass, yield it back to the user. If the validations fail, go back to the language model. Hey, that's not what I wanted. It would maybe trigger a validation error and send that validation error to the language model. Language model would then call the tool. It's just a big cycle. And this is the runtime of agents that Google defines in their paper. I think that's a great example. And there's so many different runtimes that work like this. I think a great example is Langflow. So I work at DataStax. We make Langflow. Langflow is the orchestration layer where you can add a language model and you can add tools, and then Langflow will coordinate them. It will receive a user's query, pass that to the language model. Language model would run the tools, get back the result, and then yield it to the user. Another great example of an agent runtime is Cursor, the code editor that I've been using exclusively. It's like VS Code, but with AI. Another example of an agent runtime, or just an agent, is Claude Desktop specifically. These are all just agent runtimes. And they all have the same characteristics. They receive a user's query, give that to the orchestration layer. Orchestration layer passes it to language model. Language model invokes tools if needed, gets a result, passes it back to the orchestration layer, and ultimately back to the user. Another example of this glue or orchestration layer is the Vercel AI SDK, which is a great example of code level agentic runtime tools. Okay. So far, I think we have a decent understanding of agents, but there's one piece missing, which is how do language models like call functions in user code? Right? Like, for example, if let's use the calculator example. We know that language models are pretty bad at math. They're not good at math because they're good at language. So they know when to put like plus, minus, equal signs, but the actual operations they can't perform that easily. So they also, like me, need a calculator. And so if a language model was to use a calculator tool, how does it call a function? I just described this function earlier, the multiply function. How does it know to call that function? Can a language model call a function? How does that bridge work? Well, here's how it works. It's very interesting because language models can't just execute functions. They can't execute code. They can generate language though. And that's exactly what they do. So if you send a language model, hey, I need to multiply what was it, 17 and 38, right? Then the language model is not going to call a function. It can do that. It can generate language though. And so what it's going to do with its agency is it's going to recognize, okay, I need to call a tool, the calculator. How do I do it? Well, it does it by generating text, literally just generates text. It returns you JSON, which is a language. It's not English, it's a programming language, JavaScript object notation. It returns you JSON. And this JSON is a predictable structured object with keys and values, with properties and values, with attributes. And the attributes are, depends on the model, of course, but if we're talking like pseudocode, the attributes in this JSON object are function name. The function name would be multiply or calculate, and arguments, which is an array of input arguments. And it knows this based on the schema that you provide when you tell it what tools it has. Does this make sense? So it doesn't actually call anything. It just gives you back JSON. I need to call this tool, which is this function name, and I need to give it these inputs, and it can generate all of that because all of that's just language. Like even when I use the calculator, I generate the inputs, the numbers, yeah? So it gives you back JSON, and then the orchestration layer in the agent runtime receives this string of JSON, and that orchestration layer is ideally in your application's code base. It calls the function. You write the application layer most of the time. All of the time, you write that orchestration layer. So then you receive that output from the language model, the JSON object, okay, function name arguments. And then you just like eval that. If we're speaking JavaScript, you call the function, you get the result of the function, which is either a string or something, and then you turn it into a string, and then you pass that back to the language model. Okay, I called the tool, here's the tool call result, it's this value. And then the language model reads that, which is again just language, and then continues its work. It said, okay, cool, I called the tool, I got the result, and then it will synthesize the actual answer as a string, and off you go to the orchestration layer to give it back to the user. Does that make sense? So it doesn't actually call functions, it just generates structured outputs. It just generates JSON, which it can do because JSON is a language. And then your application layer calls the function, gives the result to the LLM, and the LLM continues. I hope that makes sense. I hope that now we understand the full agent architecture. It's really very simple. It's a runtime with 3 components. An orchestration layer, usually this is your application, Langflow, AI SDK, Cursor, Claude. Tools, we talked about tools. They're just JSON objects with functions, descriptions, and schemas, minimum. And of course, a model, usually a language model. And coordinating those 3 gives you an agent. Finally, as we talk about agents, there's another thing that is a very interesting and trendy topic that is in vogue these days, which is a way of sharing tools with agents securely and in a really cool distributed way. And that is Model Context Protocol. And so we'll talk about that now. Model Context Protocol, or MCP, was introduced by Anthropic in November 24th, 2024, I believe. And so it's been some time that they announced it, but it has taken off recently. And what it is a protocol. It's a standard protocol for sharing context with models. Model Context Protocol. Wild. Naming things is hard, but not this time. And so how does it work? Well, it's a client-server protocol. So it's a 2-part system or 2-component system. You need a MCP server and an MCP client, and they talk to each other. MCP servers give context, specifically tool context, but also other context to MCP clients. And so you need something, an application that implements either one of these or both of these to be a useful MCP application. Let's talk about some use cases for MCP first, and then then dive deep into how they work and how it works. And again, we did an episode on the podcast with Jack Harrington. There's a link in the show notes if you want to dive deeper into that, into Jack's implementation of an MCP server for Create TS Router, TANstack Router app. But in any case, let's just start at the beginning with use cases. What might you be able to do with MCP? Using MCP, you could give superpowers or extended capabilities to any MCP client. Okay, what's an MCP client? Claude Desktop. Anyone use Claude? Raise your hand if you use Claude, and then feel weird because you're raising your hand in the subway or something. Sorry, it's my inner conference speaker. An MCP client is usually something of a language model, right? Like Claude Desktop is just the Claude model that runs on your desktop. Cursor is another MCP client, which is Visual Studio Code, but with a language model. And guess what? The language model is the application, rather, that uses a language model has an MCP client. Okay, so an MCP client and an MCP server. An MCP server gives context to a client. So an MCP server would give context to something like Claude Desktop. Again, Claude Desktop is just like ChatGPT. Right, it's just like an application where you can talk to a language model. You can send messages back and forth. Okay, and so if you connect Claude Desktop, which is like ChatGPT, which is also an MCP client, to an MCP server, say from Google Flights, and then you send a prompt to Claude Desktop, hey, book me a flight from Germany to Jamaica, and I want to spend $500 maximum, and it needs to be a night flight. So you send this prompt, and Claude, the MCP client, Claude Desktop, will leverage the MCP server to know, okay, so I have these tools available to book flights, and then it will use those tools to book your flight, as you on your behalf, provided the MCP server is authenticated as you and has those tools. Without the MCP server connection, Claude Desktop will just be like, as a language model, I can't do that. And so you can book flights, you can check your emails, you can summarize emails, you can book calendar events, you can whatever. Like, it can act on your behalf based on the implementation of the MCP server it's connected to. We can make this really, really, really practical with just a total real world example. I work at DataStax, and at DataStax, I created an AstraDB MCP server. Lots of words. What does that mean? We make a database at DataStax. It's called AstraDB. It's a database. It's if you're not a technical person, just think about a database. That's what it is. You can store employee records. You can store sales. You can store. It's a base of data, and so it's the world's fastest, greatest, most scalable, cheapest database, etc. But it's a database, and so oftentimes, operations people in companies need to check the database. I think HR people, for example, want to know, hey, who is the most highest performing employee, right? And so they need to open Microsoft Access or some database tool, Excel or something, and look at, okay, so they need to maybe write a SQL query and all this stuff. The AstraDB MCP server that I created connects to an MCP client like Claude Desktop, again, which is like ChatGPT, and gives it tools to act on a user's behalf with our database. And so this person now, this HR person we've invented, can open Claude Desktop and just say, hey, who's the highest performing employee this quarter? And it will, on the behalf of this person, it will open the database, do a search. It will understand what highest performing means based on its own agency. It's absolutely bananas. Does it mean the most deals closed? Does it mean the most qualified leads? Does it mean whatever? It will do it's a language model. It's an AI model. It's an artificially intelligent system. So it will already understand what best performing means in most cases, and then access the database and find employees that match that criteria, cross-referencing with other database elements like sales and stuff, and it will tell you, here's the top performers. It will literally do that. And of course, if it can't figure out what you mean by high performing, it will just ask you, hey, can you clarify what do you mean by high performing? You just type a chat message, and then it goes off and operates your database and gives you results agentically. It can do that because the AstraDB MCP server that I created connects to Claude Desktop. And so that's one use case, but you can imagine how this applies to anything, right? Like Gmail could make an MCP server, Google could, where you connect it to Claude Desktop, which again is just like ChatGPT, and you say, hey, what are my emails today first, and which ones are urgent, and it would just know what urgent means, and which ones can I defer, and the ones that I can defer, just defer them, snooze them. And that's your prompt, and you send it, and it just does that for you. That's what MCP enables. You could connect a DoorDash or Volt or Lieferando or food delivery, Zomato, Swiggy, whatever it may be. I don't know. You can connect, if they make an MCP server, you can connect that to Claude Desktop, which is again just like a ChatGPT like interface, and say, I'm hungry today. I want Indian food. Order it. Order pav bhaji and save puri or whatever. I don't know if I butchered those names. Order butter chicken and deliver it to me. That's your prompt, and it knows who you are. You already, it knows your address. It knows, and so it will go find those dishes across all the restaurants and make the order, and then respond to you with, "Cool, I've made the order. You can expect it at this time." That's crazy. That's what MCP enables. People are sleeping on this. It is so cool, and so the AstraDB MCP server. There's a link in the show notes. You can go play with it if you want, but that's what it enables. Okay, now how does it work? This podcast is about technical deep dives. How does it work? Again, we talked about agents. We talked about the agent runtime. We talked about language models. Can they actually call functions? Can they not? What MCP does is it gives context to an MCP client. Okay, how does it work? Let's start by talking about the server, and then we'll talk about the client and how they connect, and it'll all make sense. It's not difficult. It's a protocol. Okay, and so to create an MCP server, what you've got to do is write a bunch of code. Specifically, I want you to just think of a server, like a web server. It's a long-running process that listens for connections on a port. Okay? It just listens. So you start the server and it's like, cool, I'm ready to accept connections. The MCP server has two capabilities at this time of recording anyway. One is to list the tools available and the tools you write. We already talked about what tools are. They're just like functions with descriptions and schemas. So think of a server with two endpoints, if this makes it easier, like localhost 3000/list tools, and this will give you all the tools available. And the other endpoint is /call tool/tool name. So you can list all your tools and you can call a specific tool. Right? It's just a server with those two capabilities: list tools, call tool, and call tool accepts whatever inputs the tool has. That's it. That's an MCP server. Now, let's talk about an MCP client. An MCP client connects to an MCP server. You tell it how. You give it a configuration setting, and you can connect to it over the web, so over HTTP, like a web URL, like a link, or you could connect to it over just a command on your system, npx-y, some command name. This is up to you. This is up to the MCP server, but you can connect to it either way. And then when a client connects to an MCP server, is literally like you connecting to a website. Yeah, you enter the URL, you go there, and the client has initiated the connection to the server. And so Claude Desktop, for example, will initiate a connection to the AstraDB MCP server, and then you're ready for it's immediately going to call, okay, get tools. Okay, I have these tools. Great. And that's how, so over this connection, the MCP server sends the MCP client, Claude Desktop, these are the tools available. And that's it. And so then when a user sends a query, like book me flights to Jamaica, it looks up, okay, what tools do I have? Again, this is the application. This is not the language model. This is the orchestration layer, that glue we talked about. It looks up, what tools do I have? Aha, I have a book flight tool. Excellent. I'm going to ask the user for permission and then call this tool. So it asks you for permission. Do you want to use this tool? You say yes. And then it sends another request to the MCP server /call tool/tool name with the input arguments. And the input arguments are destination Jamaica, source Berlin, time night flight, max price 500, right? So it sends that to the MCP server. The MCP server on the server side does the computation, meaning it books the flight. You would pass like some authentication logic, like this is the username password, this is the authentication token, whatever it may be. So on the server side, you book the flight. And again, if you implemented the server, you wrote the code that books the flight, whatever that may be. You maybe talk to some API, you maybe do something. So the client sends this stuff to the server. Server continues the request. And when it finishes, yields a response back to the client, says, cool, flight booked. Client then receives that response and synthesizes text to the user. The server may send a message to the client like, sorry, it failed because your password's wrong or something. And then the client, of course, yields that back to the user. That's how MCP works. It's a standard client-server protocol. Some details, some nits about this is there's two ways you can operate. You can interact with MCP servers and clients. One is over standard input output, or STDIO if you're a programmer, which is just the command line interface, standard in, standard out. This is kind of bad because sometimes people log errors to standard out and not standard error. And so it can get a bit noisy, but for locally running servers, this is really great. And there's also server sent events, which is an extension of HTTP. So over an HTTP endpoint, you send JSON strings back and forth of events with an event name and a payload, and you can work with that. So you can imagine, like, the client sends to the server an event saying, I want tools, and then it sends back the tools. And then it sends you another event like, call this tool. And so it's just a bidirectional communication thing. MCP is changing in a very exciting way, because so far it had been a stateful two-way connection. And now it's going stateless, where the server is responsible for state propagation and state retrieval, but each connection itself is inherently stateless, which makes things a lot more safe and reusable and scalable. That's a pull request at the time of recording this. And so I'm not going to say more there until it's actually in the spec. But if you wanted to use MCP right now, it's going to be a stateful connection. And I can't wait to see what you build. But that's MCP. That's so it's taking AI agents to another level by making the sharing of tools and context so democratized, where companies like Domino's can just make an MCP server and have you just order food through something like ChatGPT. It's absolutely bananas. And this is paving the way for an agentic future, which is like very, very, very exciting. But this agentic future is some time away. And between now and then, there will be probably many podcast episodes documenting the development of this. The question for us now, as we sort of arrive at the end of our hopefully not too long discussion, is how can we make this practical today? Like, if you are listening to all of this or any of this and you're like, I want to do stuff. We talked about a lot of things today, right? We talked about, okay, AI is not new. We talked about generative AI, and we talked about how it works and hallucinations and things. We talked about RAG, just as like get stuff from the internet and give it as context to a model through a prompt. And then we talked about RAG on very large data sets using vector databases. That naturally led us to talk about embeddings and keyword search and hybrid search, which then led us to agents. And so we covered a ton of topics, and you might be thinking this is all cool in theory, but I'm just on a commute, man. I'm just listening to this, and you may be thinking, how do I make this practical? How do I make this actionable? And let's spend a few minutes talking about that, because I want to give you like practical takeaways. That's literally the intro of this episode and every episode on the podcast. So how can we make it really, really practical? Well, let's start at the beginning. If you want to just build anything with AI, specifically generative AI, then what you must do is start just as a user. Yeah, you could just like go to ChatGPT. Okay, play with it. Cool, that's good. Next step is you build your own ChatGPT style UI. Literally something basic. It accepts chat inputs, gives it to an LLM, and gets you an output. And you can do this. The easiest way to do this, right, is through just a web API. So you don't need to run a model on your machine. You don't need to do anything. You just like send a network request to api.openai.com/something something, and you get back. You send a request, you get back a response. If you don't know how to make a network request, JavaScript fetch is what you need to learn, and I promise you that's going to be very, very straightforward. You need something called an API key if you're not technical, and you can go to platform.openai.com to get one, and then you just send an input. The LLM over the API, over the HTTP web API, processes it, gives you an output. Congrats, you've just built your first, or maybe not your first, but you've just built a generative AI application. Next is to put a user interface on it, and you choose to do this or not. Given, do you like doing UI engineering or not? You could just make something basic. Okay, it could even be a command line. Okay, cool. You've built an application. Now, ask it a question that it can't answer. Right? Ask it a question using your new tool that requires real-time information. Ask about the current exchange rate. Hey, can you convert? Dear Lord, can you convert? Sometimes the Indian accent slips out. Indians, sometimes we swap V's and W's. Convert. Anyway, can you convert? Um, can you convert 100 US dollars to Japanese yen? Right? And usually the language model will be like, I can't do that because I don't have the latest exchange rate information. Okay, great. This is an opportunity for RAG. And so now you get to, since you already have code anyway, you get to think, how do I perform this RAG? Spoiler alert, if you're using JavaScript fetch, that's how. You just connect to an API, get it, and then feed it in your prompt. Okay. Cool. You've got RAG going. Next step is probably agentic RAG. You need to think about, I want this tool to connect to, I want this LLM rather to connect to my tools, kind of like implement the agent runtime we talked about. This is where you're going to use the Vercel AI SDK or some type of AI library or framework to do the work. And how it works is you just pass in tools. And again, tools is just a JSON object where the keys are the tool's short identifier, and you've got a description, a schema, and the implementation. Vercel AI SDK tools is what you want to implement. And by now, you probably have an agent that can perform agentic RAG, and you can just add a calculator tool to calculate the new currency. That's it. You've got agentic. Finally, you want MCP. You want to create either an MCP server or an MCP client. To do that, Anthropic has open source libraries for this. Just search for @Model Context Protocol on NPM if you're a JavaScript developer, and you'll have the server. And the Vercel AI SDK implements an MCP client, or you could even use the MCP package from Anthropic as well. And that's the way you get tools in a client and then use them. That's it. That's really the pathway. Now, for those of you who don't know how to code, it could be that learning JavaScript and doing a fetch request and all of this is an enormous effort, and you're like, I don't want to do this. Well, there's good news. There's a low code way to do this. Actually, there's a no code way to do this without any code, just a visual builder. I promise you, what I'm about to say is not sponsored. It's not sponsored. But it does intersect with my work. And I need to clarify, I'm not a shill. I'm not here telling you, hey, you go use DataStax stuff. I am merely highlighting an option of a no-code AI application builder. And also, honestly, the DataStax one isn't the only one. There's many others. But at DataStax, we work on something called Langflow. Langflow is a visual builder for AI agents. And I'll talk to you about how to use it in just a minute, but there's alternatives, and I need to be really fair to you as an audience because I don't want you to say, hey, go use our thing. Our thing, I think, is the best. I'm a little bit biased. That's why I work there. But there's tools like Diffy and Diffy, DIFY, and others that I'm blanking. N8N comes close. But anyway, Langflow. So let's talk about Langflow. Langflow, if you go to Langflow, it's exactly as it sounds, Langflow, langflow.new. There's links in the show notes. Immediately, you're dropped into a visual AI agent, literally. And what you'll see is there's components. There's an agent at the center, and there are tools that connect to the agent that it can use, a URL and a calculator, and a chat input and a chat output, because chat is your preferred interface. That's there visually. You just need to plug in an OpenAI API key. I think there should be one by default. And you can just go. In the upper right corner, you'll see a button called Playground. And if you click on this, you have a chatbot, a chat agent that can use tools. And so that should be your working basis for building your first AI agent without any code. This agent can perform RAG as well. There's a tool URL that will browse the internet. So that's a tool, and it can browse the internet. So it can retrieve and then augment its generation. It can perform RAG. It can do a lot of things. And Langflow is a great builder for visual AI agents. That's at langflow.new. This is not sponsored. I just work on this pretty often, I'd say daily even. And so there's some recency bias there. So that should ideally be something that makes all of this really practical for you as somebody who can write code and as somebody who can't write code. One thing about Langflow is it's just very interesting because once you create your workflow, your AI application, you can expose all of it, your agent, over HTTP, over an API for somebody who is writing a user interface with code to connect to. It's a very interesting tool. And hopefully these things give you tools, like actual tools that you can use to make AI applications practically. to cover everything we've talked about. Langflow also has support for like embedding stores and vector stores. I encourage you to just go play. And if you have any feedback, of course, you can leave a comment or at me on social media, and I'm happy to support. But these tools really encompass everything we've talked about and aim to make them as approachable as possible to you. And with that, I think let's land the plane here. Wow, what an episode! I really enjoyed putting this together for you. This episode is a culmination of so many talks that I've had at so many conferences with people. Like all of these things we talked about today, AI engineering, vector search, fine tuning, RAG agents, Langflow. All of this is just things that I've had. It's the synthesis of conversations I've had over and over and over again at meetups and conferences. And so this is all of that content for you in one place. I hope this has been as meaningful to you as it is to me, and I can't wait to hear your feedback, either in the YouTube comments or the Spotify comments or X, if you just at me. I'd love to hear that. I'd love to know if you want to hear more solos, or if you'd prefer guest episodes. It's really important. If you're learning from and or enjoying this content, then a great way to support it, with really no cost to you, is to just share it with your friends as far and as wide as you can on social media. If you're watching on YouTube, then if you leave a comment, guests you'd like to see, feedback you have, that's a great way to support it. While also, if you like the video and subscribe to the channel, it just signals to YouTube that this is something people care about. If you're listening on Spotify or Apple, then if you leave up to a 5-star review, that would also help. I love this stuff. I love sharing information with you and giving it to you in the hope that it amplifies your success going forward. That is the whole mission of this podcast. And thank you to the guest that canceled this week because I get to do this. And so thank you so much for sticking around. Thank you for being a part of the podcast. And most importantly, thank you for your interest in engineering.